It's good.
I apologize for the slides.
Because it's the least prepared.
Yeah. No one wants this. I don't want this. But this is in preparation for my defense, which is coming up next month at some point. Yeah. So if you're here, you don't need to come to that. So this is based on a paper that I'm working on, pretty much finished. Pretty much the same title as the talk. So I'm going to start talking about power laws, what they are, and preferential attachment graphs, which is this big class of graphs which are really popular in like the last 15 years. And then sort of define the specific model that I'm looking at, which is an edge deletion model. We'll get into that. I'll mention the results, prove some things, then mention vertex deletion, which is what I really wanted to do, but I ended up doing edge deletion because it's much easier. Okay, so a power law is basically we're looking at the number of vertices of a specific degree. So specifically large vertices. In many real-world networks, we have the number of vertices of degree k is proportional to k, basically a polynomial or inverted polynomial, k to the negative eta. So real-world networks meaning the internet. So you can make the network of all websites, and edges are links between them. That's been shown to follow a power law. Social networks generally are believed to follow power laws, but in fact Facebook doesn't. Been shown, which was sort of surprising. But real-world social networks, like just really actually knowing people instead of Facebook knowing people, that's believed to follow a power law. We have all these things like electrical networks, like the grid system, that you can see a power law, and it's all over the place. But social networks are sort of the ones that gain the most attention because they're kind of fun. And especially with Twitter and Facebook and stuff like that, they're easy to study. So we do have the data. But classical random graph models like Erdős-Rényi graphs and K-out graphs, which I've talked about here before, they have exponential tails, meaning, what it says here, the proportion of vertices of degree k decays exponentially. So most of the classical random graph models are not good enough to model these, this huge class of real-world networks, and that's a problem. So preferential attachment graphs were introduced in 2001, I think, to sort of deal with this. They, with some physicists who noticed that this seemed to be a random graph model that follows a power law. So it sort of comes from some physical intuition. I don't know why. So the guiding principle behind preferential attachment graphs is the rich get richer, meaning that we generate the graph online. So we have a graph, we add a vertex, and we grow the graph one vertex at a time. And so let's GB a graph on a set of integers, and then we add the next vertex, t plus 1, and along with the vertex, we add m edges, and each edge attaches itself to the previous vertex proportional to its degree. Yeah, that was a lot of words, but I'll show you a picture. We have this graph G here. We're adding this vertex. And here, let's just say m equals 1. So we're just adding one edge. The probability that it's going to attach itself to any of the previous vertices is given here. Basically, it's proportional to the degree. So, as I said, the rich get richer. This vertex has the highest degree in this sort of the graph of these four vertices. So it's most likely that this attaches itself to that. And that's, as a basic intuition, makes sense, I think, for for sort of at least locally, or if you think about a social network, it makes some sense that the person who knows the most people is most likely to, if there's a new person coming into the room, you're most likely to get to know the most popular person. And this seems to be the case, especially with the World Wide Web. I think it makes sense because imagine this is Google or Facebook or whatever, the bigger nodes. If you add a new web page, you're way more likely to sort of link to one of those big pages. That's sort of the guiding principle. So formally, let's go back to this part. We're defining a sequence of graphs. So I should probably say this is GT, the vertex on, the graph on vertices 1 through T. And then we're adding a vertex, getting a new graph, and so on. So this way we get a sequence. And for this sequence to work, we have to start with some graphs. So I just say we start fix some T naught, where T naught is way less than some large integer n that we choose. We generate these sequences and then we study the Gn that results. So typically T naught is, T naught could be a constant, or it could be like log n, something that's much smaller than n, so that basically the initial graph doesn't matter what happens. But we still have to mention it because otherwise we end up fine. So yeah, this is Gn, and we're going to let n tend to infinity, but just think of it as a large integer. So for this sort of...
And is the m edges that we're adding fixed throughout this whole process?
Yeah, m is a fixed parameter. And so these guys in 2002, I think it was, show that regardless of what m is, this is going to follow a power law with parameter 3. So that's this sort of very basic one where we don't delete anything and m is always the same. Then the exponent is going to be 3. So what I'm going to do is I'm going to change this slightly, and it's been done in a few different ways by different people. So to recap of what I have, well, we have here a graph where we just add m edges at every time step. But I'm going to consider a model where we delete edges sometimes. So we have this parameter n still. I'm going to assume it's 1. And because it's not that interesting to do bigger n's. So let's just do n equals 1 to make the pictures look nicer and the statements cleaner. And we pick some probability p that is bigger than 1/2. And at every time, instead of just adding a vertex and throwing in m edges, we flip a coin, or I think it's a very way. With probability p, we add a vertex and do what we did before, same thing. Probability p, we add a vertex along with edges. For probability 1 minus p, we remove the oldest edge. So let's see what that looks like in the picture. So let's say we started with our G naught or T naught was just a graph on 2 edges, sorry, 2 vertices. And then we add this vertex, it chooses something. Second step, we add some vertex again, chooses one of the previous vertices. And then at this step, this is the 1 minus p step. Having probability 1 minus p, we remove the oldest edge, meaning the edge that's been in the graph for the longest time. And I'm going to order the vertices from left to right so that basically, depending on age, the oldest vertex is to the left, the newest vertex is to the right. So we delete this edge, and then we add a new edge in the next step, and so on. And if m is bigger, who cares? Well, if m is bigger, the way I did it was we remove all m edges out of the oldest vertex that's still holding edges. If that makes sense. So we get a sequence again, GT. Now the vertex set is going to be a little more interesting. So every vertex that's been involved ever is still, even if this oldest vertex here has lost its initial edges, it's still in the graph. It can still be, the newest edge can still be pointing to the oldest vertex. So we have this set of vertices VT, which is this circle part, which is the set of sort of active vertices, the vertices that have their m edges still pointing out. So when we're doing a deletion, we're deleting the smallest number of VT. And yeah, this 1t, 1 sub t mu sub t. They're basically given by random walks. So remember, we do group probability p, we increase mu t. Group probability 1 minus p, we increase 1 sub t. And it could be the case that they sort of cross each other so that essentially there are no edges in the graph. That's an annoying thing that we need to think about, but let's ignore it. So what I'm saying is, essentially, if that happens, let's just try again. So just as a setup for the graph, we note that this is a pretty easy concentration result followed from Chernov's inequality, saying that this leading vertex mu t is going to be roughly p times t, and this is going to be roughly 1 minus p times t. So this is saying that in this random walk that defines mu t, it's always going to be pretty close to its mean. Close enough. It's going to be within square root of t, which is small here. So in the graph GT, we know roughly what the leading vertex is. We know roughly what the last vertex still holding its edge is. And we know that the number of edges in the graph is going to be 2p minus 1 times t. Okay, so these are the 3 questions that we start out with and that I answered in the paper. So given any vertex and integer k, what's the probability that B has this degree? So basically finding, for any fixed vertex, finding its degree distribution. Second question is similar. So the degree sequence is basically the list of all degrees in the graph. So for every vertex, you write down its degree, you get this long list. And so the question is, what is the degree sequence? And this is where we find out if we get a power law. And there's a subtle difference between A and point 1 and 2. Point 1 is just for any fixed vertex, what's the distribution. 2 is basically summing up the distribution over all vertices, which we'll see. And third question is sort of a more general question where once we know the sort of degree and the degree sequence, we can start exploring it and see what does the graph look like and is it connected. Are there any questions so far on the model, how we generate this graph? Okay, so the first theorem, which is what I'm going to spend some time proving, or just convincing you of, the degree distribution. So still, if n equals 1, this is the degree distribution. So essentially, for every vertex V, the probability that it's k is either, the degree is either going to be 0 or it's a geometric distribution. So if we ignore the QV here, maybe you recognize the geometric distribution, which is sort of the discrete analog of the exponential distribution. It's a well-known distribution. So what can I say here? Yeah. The proof is going to have it's going to use CMJ processes, Crompton-Jarvis processes, which I talked about last time. Yeah.
When you described, you said random graphs have exponential degree sequences, right? So that seems like it should be a lot less than the power law, right?
Yeah.
The degrees are generally smaller. Right?
In a classical random graph. Yeah.
Right. So these the preferential attachment graphs, whenever I add new vertex, I'm only adding one edge.
Yeah.
And with the random graph, you add a proportion of the possible edges, right?
Oh, I see.
So it seems like there should be a lot more degree in a random graph.
So generally, yeah, this is the mistake I make. I always work in sort of sparse graphs, meaning that the number of edges is always linear. So on average, if we're going back to what I said about degrees, that only applies when the average degree of any vertex is a constant. So in some random graphs, if we're talking about Erdős-Rényi graphs, we could have graphs where the average degree is log n or something, and then what I said doesn't apply anymore. So what I'm saying is basically, so you're thinking of the graph where you include every edge with probability p.
Yeah.
So what I'm saying applies when p is like a constant over n
Okay.
in that region. So yeah, that's a very good point. That's the only interesting. That's all the random graphs I work with are in that region, so I forget that. Various histograms. Okay, so what I thought we were going to ask is, yeah, this looks exponential, right? Or this looks like it's going to decay exponentially. For large k, this is clearly decaying exponentially. Even though that is the case, this formula is actually going to give us a power law, which is sort of surprising to me. We'll see why it happens. Okay, if n is bigger than 1, basically what we can do is, instead of looking at this graph where every vertex adds is added along with one edge, or we can do that, basically the same thing, and then merge groups of m vertices together. That's sort of something I proved, that basically the only interesting case is that there's one, and then we get higher ends by just merging vertices together. So we don't really need to care about it. Okay, for the degree sequence, turns out there's a phase transition.
So, like the sum of n variables, so they're independent, right?
Yeah.
And the parameters, they are not the same? Or the same?
They are the same.
So they are all the same PVs and QVs?
So for that group of n variables, they are the same. Well, so the group, those m vertices are going to be close enough together that the difference is going to be very small, insignificant. So there is a slight difference in the QVs when we're summing up m vertices. There's a slight difference, but m is always like a fixed number. It's like 10 or something.
Yeah, I get that m is fixed, but you're saying that all the parameters, they're all the same. For
these PVs and QVs depend on the vertex, but when we're doing this grouping together and vertices that are close to each other, they're close enough that we can basically treat it as equal for those m vertices. But then if we're going, somewhere very different than the graph, it's going to be different. These parameters basically depend on how long the vertex has been in the graph. So if we're doing m vertices that are right next to each other, they've been in the graph for essentially the same amount of time. Degree sequence. So this is where we talk about the power law and so on. And it turns out there's a so-called phase transition. So the parameter p, when it's below a certain value, which is roughly 0.83, we get an exponential tail. Here alpha is some constant less than 1. So in the region where p is small, we get this sort of undesirable thing of classical random graphs. So the sort of point of preferential attachment graphs is to get the power law, and we get it when p is bigger than 0.83. It's kind of interesting to me that it doesn't depend on the parameter m. So this is depends only on p. And we can choose p to get any exponent eta that we want. Yeah. And then the structural theorem, basically the last question I had was, is the graph connected and so on? It's not connected, but a classical thing in random graphs is this sort of giant component. Now it doesn't matter what m is. So when m is equal to 1, we just get small components everywhere. Size root n is considered really small in a graph of n vertices. And when m is at least 2, we get one component that contains a positive proportion of all vertices, and every other component is size log n, which is like minuscule. So when m is at least 2, we do get this giant component where I shouldn't say almost all, but no, definitely not. But there is like one major component that where sort of all the interesting stuff happens, and everything else is just small trees essentially. everything I say happens with high probability, meaning that as n tends to infinity, the probability tends to 1 that these things are. There's always a possibility, that we get something weird, but probability tends to 0.
So, what's the big omega?
Oh, big omega means basically it's order n or larger.
So it's super.
No, so it couldn't be more than linear. So it basically it's bigger than alpha n for some positive constant alpha. So this should be read as the component contains a positive proportion of the vertices. Like meaning a certain percentage of the. Okay, so let's talk about the proof of the degree distribution. So going back to this thing here, we're fixing a vertex V and we want to find the degree of it. So this is where I had a really nice movie to show you animation, but we'll do without. So we talked about CMJ processes last time, prompt mode joggers processes. If you don't remember, it doesn't matter because I'm just going to give you a 5-second summary of what happened. So first of all, we note that when we're saying that we pick a vertex with probability proportional to its degree, that is the same thing as picking one edge uniformly at random and then picking one of these 2 endpoints. I think that if you think about it, not too hard to see. So basically, when we sum up, if we sum the degrees in a graph, we're going to get every edge is going to be counted twice. That's sort of the underlying fact in this. So instead of thinking of it in terms of an edge choosing a vertex proportional to its degree, this picture is supposed to show you that this edge here, it doesn't choose this vertex, it chooses this edge, and it chooses this half of the edge. So if you're looking at this picture is a picture of edges adjacent to V. But I've drawn them in this way to show that this edge chooses this edge, specifically this half of the edge. So in this way, we sort of get a tree of edges that are adjacent to V. So there's more information. If we know that an edge is adjacent to V, there's more information to be found, which is which edge did it choose in order to become adjacent to V. So we're keeping track of this. We're making up a tree of edges. So these, in this picture, m equals 2. But so these 2 edges that were initially adjacent to V, they form roots of 2 trees. So this edge here, it has 1 child, and then that one has 2 children. So think of family trees, that kind of thing. This here is the root of another tree, with just other edges hanging off it. So hopefully this picture explains it, because if I try to say it in words, it's kind of confusing, because it's a tree where the nodes are edges and so on. Okay, so what we note is that for the degree of V to increase, so initially when we sort of start, when we insert V, it has these like m edges going out. And we're going to think of it in terms of like when does the degree of V increase, or when can it change? So for the degree of V to increase, there has to be some edge that chooses one of the edges adjacent to V. Now we're back to n equals 1, by the way. So V comes in with 1 edge, and then waits for some new edge to pick that edge. And at every time after V is inserted, the probability that a new edge does choose the one edge that's out of V is roughly 1 over 2 mu t for some constant mu. If you remember, going back, I said the number of edges in graph GT is always 2p minus 1 times t, roughly. So it's always about a fixed number. So we can figure out what the probability, whenever an edge is coming in, it chooses one out of these mu times t edges, uniformly at random, and then one of the 2 endpoints. So the probability that it chooses this edge that B has, and also chooses the right endpoint of it, is like 1 over 2 mu t. So right now we're just looking for this, sort of the time until the first edge chooses us. So I'm the vertex V, I have an edge, and I'm just waiting for one of the new edges coming in to pick me via my edge. And let that time be t sub e. And basically it's just going to be the probability that it doesn't happen before t1 is product of 1 minus 1 over 2 mu t. And then this approximation is just basically the harmonic series approximation. And from this we can read off that log of TE is exponentially distributed. Okay, this is something. But exponential distributions are nice. So if you remember Poisson processes, so what's going on here is I'm waiting for something to happen. And the time until that happens, well, the time until it happens isn't exponentially distributed, but the log of that time is exponentially distributed. So for Poisson processes, that's exactly what they do, right? We're waiting for something to happen. The time until it happens is exponentially distributed. So basically, if we're transforming time here, looking at the log of times instead, the time until some edge chooses me is going to be a Poisson process. But the time is when someone chooses. So here we're just setting up some notation. I don't know, we don't really need this. Well, I guess, yeah, the point of this slide is to show that we can sort of scale time in such a way that if I'm inserted at time 0, I die at time 1. So every edge, yeah, if an edge is inserted at time TE, then we expect it to be removed at time gamma times TE. That follows from the concentration that I mentioned before. We can, at every time, we know pretty much which vertex is inserted and removed. So we just scale time. I'm not bothered with the details. We scale time so that every edge is in the graph for time or unit time interval, essentially, under this transformed time. So we get to this nice picture, which may look familiar if you came to my last talk. So let's say this is the initial edge E I was inserted together with B. It's in the graph for a time of unit length. What do you say? I mean, unit time. It's in there for 1 minute. And then new edges choose that edge according to a Poisson process. And every edge that chooses the edge itself gives sort of new edges an opportunity to pick me. So if we're going back to this picture, we're waiting, and then some edge chooses us. And then that edge also sort of exposes itself to new edges coming in. So now me, my original edges, and this edge are all sort of waiting for edges to come in. So every edge that chooses me via one of my edges starts a new process. And these processes pretty much work independently of each other. That takes a lot of work to actually prove. Let's see. So we get this picture where we have a Poisson process of length 1. Every rival in it gives a new Poisson process of length 1, and all these act independently of each other, and every arrival gives a new Poisson process. This is exactly what I was talking about last time, which is these Markov-Joggers processes. So this is the transform time scale. So we're interested in, at any given time, so at time, let's say I was inserted at time t0. We're looking at time, whatever, there's, and the transform time 1.5. Then my degree at that time is going to be the number of edges in the graph at the time, which is equivalent to the number of active processes at that time. So my degree can go up and down, right? Because edges come in, edges get deleted, and it's going to exactly follow this picture here. So in this case, at this time, the degree would be 4, because there's 4 active processes. I don't know how much I actually proved at this last time, but this CMJ process, it has this sort of almost geometric distribution that we wanted to prove. And then this Q sub v that I mentioned is actually these functions. I don't really want to get into what those functions are. They're really ugly, but yeah, that's how you get it. So the key sort of observation is this, when we're waiting for a new edge, under this transform type, we can see it as a Poisson process. The edges that choose me via my original edge. And then every new edge itself gives a Poisson process, and so on. Moving on quickly to the degree sequence. We define alpha. Who cares what it is? Oh yeah, so alpha is this constant that only depends on p, actually. Even there's an m in there, but it cancels with the mu. Alpha is going to be the expected number of arrivals in a Poisson process. It's the rate of all these processes. When alpha is bigger than 1, then we expect more than 1 arrival in every Poisson process. So then we sort of expect this tree of processes to sort of expand exponentially. So this is going back to branching processes, which I mentioned last time. Basically, each there's a breaking point. So this phase transition that I'm about to talk to is about the breaking point where we expect more than 1 or less than 1 birth out of every process. If we expect less than 1, then this is quickly just going to decay exponentially. It's just going to die out pretty quickly, this process. If every Poisson process expects more than 1 offspring, then it's very likely that this is instead going to grow exponentially. So that's where the phase transition comes from in this graph. So if we look at these functions p of t and q of t, don't bother with the details here, it's just to note that when alpha is less than 1, this green function converges to some positive constant. When alpha is bigger than 1, the blue function converges to some positive constant. Meaning that this expression is going to be, it explains why this behaves so differently when alpha is less than 1 and alpha is bigger than 1, essentially. That's the takeaway from this difference. And you can also see how annoying these functions are, like this weird whatever.
Why is that?
It's just an ugly function. It's an infinite sequence of like ODEs that you have to solve, and each one depends on the one discussed. But they essentially decay exponentially to some constant. So as long as we're staying away from this initial business, then we can pretty much figure these out, which is good because we want to solve this integral. So the degree sequence, we get it by linearity of expectation. We can just, the number of vertices of degree k is just summing over every vertex the probability that that degree is equal to k. This is a very nice thing about expectation. It's linear, so we can just do this. And then we sort of had to rescale things in order for this integral to work out, so we get this gamma to the t here. But essentially we get this integral. Because these two functions behave so differently, this integral is going to be quite different for large k, depending on whether or not we're in the alpha is bigger than 1 and alpha smaller than 1 case. Okay, so now moving on to the giant component. I just quickly want to introduce this concept of a master graph, which is very nice. If we want to get into like the theory behind the proofs, this is a nice concept. So imagine we do this whole process, and then we keep track of all the edges that we removed and place them back in the graph at the end. Get this graph gamma. This graph is going to contain all the graphs that we generated so far. And instead of doing this whole thing where we generate, add, delete edges, and so on, we can actually just start by generating the sequence of additions and subtractions. So essentially, we start by just generating a random walk or a sequence of pluses and minuses, essentially. If we just condition on that, then we can, instead of doing the thing with adding and deleting things, we can just actually generate this gamma from the get-go. It's not actually that hard to generate, which is really, really helpful. Instead of having to go back all the way to the starting graph, do everything, we can actually do a thing where we can generate it from the other direction. We can start with the last vertex. So again, we fix the sequence of pluses and minuses. That's vital. Because if we have that fixed, we know exactly at any time, we know exactly the number of edges that's going to be in the graph. Because if we fix the sequence, then we know which vertices have an edge coming out. We don't know where it's going, but we know exactly which vertices will carry an edge going out at any time. So this picture, what this picture is supposed to show is that this is the initial fixed graph. We still have to start with something that's fixed. So we start with just a K2, just two vertices, one edge. And then every sort of random edge is free in the beginning. So we're just drawing it as some arrow into the void, not going anywhere. So I'm just going to show you how to generate this from the other direction. So let's say we want to figure out where this edge is going, the last edge. And from sigma, we can figure out that, okay, well, at the time that this vertex was added, we'd already removed all these edges. So we can just see from this picture, okay, exactly this edge can choose one of these edges. We don't know where those edges are going, but we can just commit to one of them and see what happens. So we draw randomly out of these four options. So there are two edges, both of them have two endpoints. So let's say this happened. The edge shows the sort of the free endpoint of this previous edge. So all we know now is that this edge has committed to wherever this edge is going to go, but we don't actually know where it's going into. So we have this picture. Okay, let's figure out where this edge is going. And again, from sigma, we can figure out exactly which edges were in the graph at that time, and we pick something. Pick this. And now the previous edge, the one that committed to following this edge, does follow to where we're going. So this is an extremely helpful tool. So basically, when we're doing this thing with the giant component, or basically any sort of exploration in this graph, it's very useful to start with nothing generated at all, and just pick one vertex and do a small local search. So we can figure out the neighborhood of a vertex, or figure out what's happening around the vertex, without really revealing basically any information about the graph, except for the small amount of information that we need. So that's the tool. I'm not really going to talk about the proof. But I'm going to note that if n equals 1, then this gamma is a forest. And the roots of the forest is exactly specified by the initial graph. If we go back to this picture, gamma here is just a tree. And that's always going to be the case, because we start with some graph. Well, I guess it's possible that the what we started with contains a cycle. It's not a tree. So assume that the starting graph was a forest. Then at any point we're just adding one edge. That's never going to take us. That's never going to add a cycle to the graph, essentially. So if we start with a tree or a forest, then gamma is always going to remain a forest. And then if we want to figure out what GT is, what we're really interested in these graphs, GT. But since the gamma contains all of them, then they're also all going to be forests. And, well, I didn't really, I did plan to talk more about this. I sort of broke off in the middle. But basically what you're doing then is, so for n equals 1, we just have forests. It's not that complicated to see that all the forests are going to be very small. So what I said was when n equals 1, we just have these small components, nothing large, because it's just these forests. Every component is 3D random. But then when n equals 2 or larger, what I said before, we think of like merging vertices. So then if a tree contains 3 vertices, if we merge each of those vertices with its closest neighbor or whatever, let's say n equals 2. And then those vertices are also in trees. And then we can sort of do this thing where we start with one tree, and then we find neighboring trees, and then more and more trees. And we get this sort of whole branching process on these trees that help us build large components. That's a very short way of saying it, but that's the idea. Okay, so future problems is, well, exactly how large is the giant component? I wasn't able to answer anything really good when it comes to that. I just know that there exists a linear sized component of order at least n, but you would be interested in like exactly how large is it. That's very hard. The structure of the graph, so what's the diameter of it and stuff like that. There's so many questions you can ask about a graph. Yeah, and I have no idea. And then other ways of removing edges could also be important or interesting. So in this case, I mostly talked about n equals 1, but when n equals 2, I assume that we always remove the 2 oldest edges. You could do a thing where you pick a random amount of edges. Maybe not always take the oldest edges. Maybe take a random edge, remove it from the graph, that kind of thing. I don't really know what would be interesting. This is barely interesting enough. So this is the problem that I really wanted to work on. I'm going to finish everything with this vertex deletion. So instead of removing edges with probability 1 minus p, we just remove the oldest vertex and every edge that is adjacent to it. So basically same thing, but yeah, remove edges. So same questions: what is the structure? What's the degrees and so on? And the annoying thing here is the really big challenge is just show that the number of edges is concentrated. So this thing that I pretty much glossed over in the previous, for this thing, that everything is concentrated, the number of edges is always around 2p minus 1 times t. It's really easy to show. That is a huge hurdle in this case. And so what I did was I spent maybe 2 months on this and proved a bunch of things assuming that this was true. And then it turned out to be this whole thing that I just can't figure out. So if you want to work on this, talk to me, because I have some results. Okay, any questions? Yeah.
So are there models, so all of these models for getting power law, that exponent was less than -3?
Yeah, I think that's, let's see. Did I say something wrong here? So there's a theoretical bound at like 2, right? Wait.
Well, I was just going to ask if there are other methods to get power laws like greater than -3, right?
Yeah, so the one I got was everything greater than 3 is achievable with this model. I think there are other models that get other results. Yeah, there have been a bunch of different variations on this where you can combine it with other random graph models, or you can do deletion by other methods. Like Alan has done a thing where you delete the vertex with highest degree, for example. Stuff like that. And yeah, there's a bunch of different things. And yeah, I don't know, because there is a theoretical bound for what the exponent could be. I don't remember. But I don't think I hit it. Yeah. Typically, by the way, real-world networks, I think, have this exponent is between 3 and 4. I don't remember. I've read somewhere that like they tend to fall in this specific range. I do want to mention one thing that I probably should have included. So you might, like, one thing I wanted to find, when I saw that this had this phase transition where sometimes you get an exponential tail, sometimes you get a power law. I wanted to find sort of a real world context where, depending on some parameter, you do get different different tails for the laws. And I did find one example. So if you look at last names in Japan, they do follow a power law. And I think this is true in a lot of countries. The distribution of last names, the most common last name is, they follow a power law. But in Korea, they have an exponential tail, which I thought was really interesting. So there's some cultural parameter that changes, which is this P, I guess, between the two countries, where one of them has an exponential tail and one of them is a power law. So there might be somewhere where you can apply this, because I think I haven't really seen any other examples where you do get this interesting phase transition where it's actually different for different parameters. So that was kind of fun. Any other questions?
Was there any kind of clear parameters in your model that you could, so you had this transition at P + 0.83. Was there some kind of parameter that was easy to shift that would move this transition P to something else?
Do you mean if I could introduce something else to the system?
I mean, I don't know, is this P somehow natural, or is this P somehow or an artifact? Because there's some parameter here that we can tweak that's not
Well, it comes from this alpha thing, the expected number of, basically the expected number of edges that choose my original edge before it disappears. So, depending on whether or not that's less than or more than 1, that's where the phase transition happens. And that's sort of, I guess that is always going to be a pretty direct function of P. Right. I don't know if that answers the question. Any others? Okay. Yeah, the defense is going to be, I think, January 26th. It's not totally set.
I'm taking